I now want to do a two-dimensional momentum problem example, and I'm going to do it two different ways. I'm going to do it graphically, considering that you're using your geometry instrument to solve the problem, to scale, and then we'll do it trigonometrically after that. So the problem is a 1,000-kilogram car moving east at 20 meters per second on frictionless ice. Okay, so it's sliding, colliding with a 4,000-kilogram, 4 times the mass, truck traveling at half the speed, 10 meters per second, southwest. So after they collide and they stick together, does that say that there? No, well, they stick together. Okay, so it's an inelastic collision. What is the velocity after impact? So here we go. The scale I'm going to use to fit it on your piece of paper, so to speak, is 1 centimeter is 4,000 kilogram meters per second. And so we have the momentum of the car. Mass times velocity, 1,000 times 20, 20,000 kilogram meters per second. So how long of a vector is that going to be? That's right, 5 centimeters. 5 times 4,000 is 20. Okay, for the truck, we have a 4,000 times 10, so we have 40,000 kilogram meters per second. It's got twice the momentum, half the velocity. That's 10 centimeters. So all this should fit. So let's go ahead and draw a reference line with our starting point. And let's draw the momentum of the car. There it is. Properly scaled, hopefully. And then producing a 45-degree angle from that, we're going to add the truck vector to it. There it is. The truck vector. 10 centimeters, 45 degrees, due southwest. So the resultant is simply this. There's the resultant. That's the total momentum before, because it's the addition of the two vectors, the car and the truck. The vector addition is the total. We're assuming that the car and the truck are in isolation. They're the only objects interacting. And the Earth is not interacting right now from the standpoint that it's frictionless ice. Obviously not very realistic, but gets the point across. Since this is total before, it's also total after. So let's go ahead and remind ourselves of that. That's the momentum afterwards. And from this, we're going to get the velocity. So be careful not to confuse momentum and velocity. Getting the momentum, we just went through the graphical work, and it should measure to be about 7.5 centimeters if you're doing this to scale and doing a good job with it. And the angle should measure about 74 degrees with respect to west. So that'd be south of west, right? So total momentum before is total momentum after. That's 7.5 centimeters times 4,000 kilogram meters per second per centimeter. So centimeters goes away and we have the kilogram meters per second, 30,000. That's 74 degrees south of west. So there's our momentum. But that's not the answer. We're looking for the velocity. The velocity is momentum over mass, so divide by the mass. Now mass is a scalar, so it doesn't affect the vector momentum. So I'll rewrite that in total here. Dividing by the mass, but it's not just the mass of one, it's the total mass that's moving right now that has this momentum. They're stuck together. So that gives us 6 meters per second, 74 degrees south of west. There is our two-dimensional example. Now let's do it mathematically. So, for the trig solution, we want to start by drawing ourselves a freehand sketch. Mine will look pretty nice because, well, I'm doing it on the computer. But you don't have to worry about scale here. You can just do this quickly. You really should do a sketch, though, because you will get yourself into trouble if you don't. Momentum of the car, 20,000 kilogram meters per second. I was going to say kilometers per second, which is directed east. And then added to that, we already know about the truck vector, which is 40,000 kilogram meters per second. All right, so there it is. And we know that the resultant is the combination of the two. So that's what we're trying to find. We're going to do it mathematically. So the sketch will help us because now we're going to resolve this component I should say, this vector into its components. I mean, this is a component of the resultant, but anyway, with this 45-degree angle, let's resolve it into its y and x components. That'll be helpful. 45-degree angle there also. Okay, so in the y direction, we have 40,000 sine of 45 degrees. So that's what this is. Hypotenuse sine of 45. And that gives us 28,300. Since it's 45-degree angle, it'll be the same for the x component. So there's the x component as well. Now, the car momentum is already just an x component. It's already resolved. There's nothing to resolve, actually, because there's no y part to it. So now, the next step is to say, what's the sum of the momentum in the x direction, the momenta? And we just add them, but we add them properly. So we have the car is 20,000, but then the x part of the truck momentum is in the other direction, so we subtract it. It's in the negative x, giving us negative 8,300 kilogram meters per second. So that's the total in the x. See, I want to clarify. Momentum is conserved in each dimension. There. So now in the y dimension, let's do the same thing. Well, we have 0 for the car, because there is none, and minus 28,300 for the truck, giving us minus 28,300 kilogram meters per second in the y direction. So now we have the components, and now our goal is going to be to construct a right triangle, because right triangles are wonderfully easy to work with, of this new momentum situation where we have the sum in the x and the sum in the y. We know how big those are, and the resultant is this. Notice that resultant is exactly the same as our original. It has to be. But now these components are just perpendicular components, making it real easy. Yes, you could use law of sines or cosines, but I'm not going to do that. So there's the total. And we're ready to find the magnitude of the total. Since it's a right triangle, we can just use Pythagoras to help us. So the square root of the sum of the two parts gives us 29,500 kilogram meters per second. And the angle will just do inverse tangent of y over x. They're both negative. So negative 28,300 over negative 8,300. And we get 73.7 degrees south of west. So our final answer for the velocity is express the momentum over mass. We'll fully express the momentum. 29.5, 73.7 degrees over 5,000, giving us the final answer, 5.9 meters per second at 73.7 degrees south of west, which is very close to the graphical method solution, but this of course is a little bit more accurate. And in general, I would say that you can use the method that will give you the easiest answer. Well, that seems most applicable to use, unless it's very clear that you need to solve it one way or the other. If you consider the amount of effort with both of these methods, you might conclude that the graphical method was easier than what we did here. But that's not always the case. Anytime you have a right triangle, then using trig lends itself quite readily. But if it's complex angles, then it might be graphically might be the better choice. So there you go. That's a brief summary of how to analyze a two-dimensional momentum problem.